Good morning, good evening, wherever you may be, across the nation or around the world. My name is Shane Squarick, and on behalf of the Illuminating Engineering Society, I am pleased to welcome you back to another webcast as part of our educational webinar series. Today, we are pleased to welcome Robert Karlicek Jr., PhD, as he presents Smart Lighting is a Myth, LEDs, Illumination, and Future Possibilities. Robert F. Karlicek Jr. received his PhD in physical chemistry from the University of Pittsburgh. Prior to joining RPI, he spent over 30 years in industrial research and R&D management positions with corporations including AT&T Bell Labs, EMCOR, General Electric, Gore Photonics, Microsemi, Luminous Devices, and Solid UV. Bob's technical experience includes epitaxial growth of high-performance LEDs and lasers, advanced device fabrication, and high-power LED packaging, thermal management, control systems design, and applications in solid-state lighting, as well as other novel LED uses such as IR and UV LED applications. Bob is well known globally as an LED industry expert. He is a frequent presenter at conferences and workshops and has over 40 published technical papers and 24 U.S. patents. As always, we welcome you to submit your questions throughout the duration of today's presentation using the chat box to the right-hand side of your screen. In the interest of time, however, we may not be able to acknowledge all of your questions until the end of the formal presentation. Your participation in today's live webcast does qualify you for a continuing education completion certificate, which will be automatically emailed to you within the 2 weeks following today's event. All of our webcast presentations are recorded and made available on our website exclusively to IES members. To become a member of the IES, visit www.ies.org or send an email to membership@ies.org. With that said, it is without any further ado, I am pleased to turn the floor over to Bob Karlicek.
Shane, thank you very much for this opportunity to present. And I'd like to just take a moment to say that as the director of the Lighting Enabled Systems and Applications Center here at RPI, I've been privileged to work with a large number of professors and very smart students at our companion schools, Boston University, the University of New Mexico, and Thomas Jefferson University. The center operates with funding from the National Science Foundation, New York State, Department of Energy, and also the Department of Energy and the federal government. And it's because of these collaborations we've been able to take a look at what smart lighting is and where the lighting industry is going as a whole. So let me talk a little bit about the outline. I just want to mention very briefly a little bit about LED evolution and where we stand at the present time. Explain why I think our current definition of smart lighting tends to be a little bit mythological, and what we would need to do to be able to make lighting systems truly smart. One of the things that we'd like to talk about at least is making cognitive lighting systems, and that's part of how we get to lighting systems that think. And so with that, let's talk a little bit about light-emitting diodes. Light-emitting diodes were invented in the 1960s in the form that we know them now. And in the mid-1990s, the Department of Energy and other people around the world started looking at, with the advent of blue LEDs, how we could now start charging after solid-state lighting. And since the year 2000, approximately, the Department of Energy has had a solid-state lighting program, taking a look at how to really drive energy-efficient lighting with LEDs. And they've put together a roadmap for the last several years, projecting the luminous efficacy of where LEDs can really go. A lot of interesting problems have been solved with government funding and funding of industry going after the market opportunities that solid-state lighting represented. And as people have pushed the luminous efficacy up, LEDs have just gotten better and better, but they're starting to get to some logical endpoints of their technology capabilities. Even though the Department of Energy forecasts phosphor-converted LED, where that question mark line is at around 250 lumens per watt, it's my opinion that they're really not going to make it there, because the LED technologists in industry have largely tried just about every technological path to solve some final problems in making LEDs more efficient than they are today. And they just haven't been able to crack that nut. And so I think that blue bar, which is right around where we are right now, is going to be the limit of what we can get in the near future. Also, the LED companies, the people that make the LED chips, have no real incentive to improve the efficacy. Their businesses are largely commoditized already. Their operating profits are very, very low for actually making the LED chips themselves. And so to really invest in a lot of new technology to get incremental improvements in efficacy are just probably not going to happen. So as a result, today's LED lumen per watt is about as good as it will get. Meanwhile, the LED companies are charging after technologies like micro LED for advanced displays. So where the improvements in the future in terms of efficacy are going to come are going to be lumens per dollar at the fixture level, but more importantly, lighting systems with controls that allow us to not waste light. That's where the future is going to go for advanced lighting systems. And so with that, let's talk a little bit about why I tend to believe that smart lighting is a myth. Here is a typical web graphic talking about the future of the smart home. You find out that everything is forecast to be connected to everything, and the house can pretty much operate by itself. Note that one of the larger icons in this smart home are so-called smart lights. But in this embodiment of a smart home, the human is still in the loop. You have a phone that can control the lights, although in all honesty, I don't know why you would want to do that. You can talk to Alexa or some other smart device to control the lights, but the lights just do what they're told. They're not really smart. They may be connected, but they have no intelligence of their own. They're not really aware of their environment. And so they can't really function autonomously. They emit photons, they emit light, but the light doesn't know where it's going or what it's hitting or what the environment requires of the light bulb. Today's lights just simply do what they are told to do by others, other smart systems in the home, or even in commercial or industrial workplaces. So we really aren't at the point where the lighting systems are smart. Connected, yes, but not smart. And so it begs the question of what we really need to do to realize an entitlement that we could get to by making lighting systems truly smart. And for that, I like to draw the analogy to smart systems that we know are coming down the road. And so I like to show this example of a smart autonomous vehicle. Essentially what you've got is a car with a lot of sensors. That's that pod network that you see on top, looking around to find out where the road is, and an embedded driving expert. That embedded driving expert essentially operates the car, and people advertise that this will produce a great improvement in car safety, better fuel efficiency, people can relax and read a book while they're in the car, better traffic management because the cars can be scheduled by talking to the cloud, and even better smart city management because now we can schedule traffic around people going into the city and getting out of the city. So this is part of the promise of autonomous vehicles. The question that I would ask, and that we've asked in our center for the last 9 or 10 years, is how would we get to autonomous lighting? So the advantages of autonomous lighting would be optimized energy utilization efficiency. It would be ergonomically aware, the right light, the right spectral power distributions, the right kind of illumination for the tasks at hand to be able to help people perform better in their jobs or be more comfortable at home. Take a look at how we localize light quality so that not everybody needs to be exposed to the same amount of light in their particular place in a workforce or an office building. And then other interfaces to smart building controls, smart city controls, things of that nature. In the same sense, we're talking about autonomous lighting as being a lighting system that has an embedded lighting expert. That is to say, the lights know what's going on, they know what they need to do, they optimize the illumination for the work at hand and do not require direct human engagement. They can engage with humans through normal spoken words or hand gestures, but they generally will operate by themselves. So taking the analogy one step further, I've taken a look at how we might be able to create similar systems definitions. And the Society of Automotive Engineering and the National Highway Safety and Transportation Administration have a definition for what they call the different levels of autonomous vehicles, level 1 through level 5. And level 1 basically is just driver assistance, but the driver's always on. They take full control of everything that's there. There may be a few warnings or things of that nature. Level 2 would be things like cruise control that you've got now. And they go on down the road to talk about feet off, hands off, eyes off. And of course, the end goal is the fully autonomous vehicle at level 5, where the mind is off. The human is now no longer really engaged in the driving process. So I've taken a crack at defining a similar set of levels over a very similar time frame for autonomous lighting. So as I mentioned, the lighting doesn't know what it's really doing. It's connected, but it doesn't know where its light is going. So at level 1, it's occupant operated nominally. The lighting system itself is oblivious to its surroundings. Level 2 is kind of where we're going with instructions that we have through Alexa or Google Home or other smart devices where it's listening. Level 3 would be sensing. Level 4 would be adaptive spectral power distributions autonomously. And then 5, adaptive distribution, or what we call cognitive lighting. And so this is kind of a parallel that we can take a look at. And this hierarchy might be of interest for the lighting community to consider as we take a look at driving continual functionality in the future of lighting systems, especially with controls and intelligent systems development. So there's a possible role there for the IES. There's a possible role there for other lighting designers and lighting companies. And I think that this analogy would bear some scrutiny. So how would I define a smart lighting system? Well, the way we've done it at LISA is to define a lighting system that uses reflected, encoded illumination to sense its surroundings. It's much the same way an individual senses their surroundings, because what we do is we see with our eyes, and what our eyes detect is reflected color-encoded illumination that tells us what and who is around it and what is happening and where things are going and where things are. But can the lighting system do the same kind of thing? We would make the argument that it can, but it would collect light in a different way. The little cartoon on the right-hand side simply says that lighting systems really cannot control what they do not measure. And that's maybe one of the hallmarks of today's lighting control systems, is because they don't really measure lighting. They take other information and attempt to control the lighting, but they can't really control it properly. And so that's why lighting control systems generally, as a rule, are not really found to be favorable in a lot of commercial building applications, where commissioning issues, use issues, complications tend to make them obsolete shortly after they're installed. So how can we collect light information to characterize the environment, and how can we use that information for improved lighting and building services? And that's kind of what we've been looking at. How do we give sight to light? And so our approach has been, and what we call our three-legged stool, is to work first of all with digitized color tunable lighting. Light that can transmit data, light that can change color. And so we have a powerful light source that can meet the needs of people, but send out digital IDs so that systems can recognize what the light is doing. We pair that with advanced light sensors that take a look at reflected light. They take a look at the data in the reflected light. They take a look at the color of the reflected light. And even though they don't see like people see, they see enough of the environment to figure out what people are doing, where things are, whether or not there are windows in the building with sunlight coming in, and adapting and sculpting the light profiles to meet the needs of people. And they do that through controls and communication networks between the lights and other building systems, and a little bit of machine learning, because these systems should be able to adapt to changes in the environment and recognize scenarios that allow them to go back to lighting profiles that were found to be valuable in previous lighting experience. And so these are the three key components that we see as really important for creating autonomous lighting systems. So the data transmission, widely tunable light sources, and one thing I didn't mention, these light sources ideally should be beam steerable. And more people are working on beam steerable lighting. So instead of having multiple kinds of fixtures to deliver different lighting scenarios depending upon what's required, you would just be able to have one fixture that would redirect its light. Advanced light sensors that look at reflected spectral power distributions and reflected data. And then finally, advanced controls. At the center, we look at having them be Li-Fi capable, which is essentially Wi-Fi but with light. We use a robotic operating system, which is an open source system. There's nothing says that robotic operating systems can only be applied to robots. And they have certain advantages over many of the operating systems that people use today for lighting and building control. And then finally, building management system integration. So this is the platform around which we've been looking to develop and explore the possibilities for lighting systems that think. Shown another way in a cartoon over here, and even though the student that designed this simple graphic used an incandescent light bulb as the light source, this is where we would have a person in a space. All the surfaces are reflecting light. The light is encoded. The squiggly red lines show that. The light sensors are looking at reflected light color, reflected light data, and it can tell the difference between the internal light sources and ambient light from a window simply because the sunlight is not modulated. And so all of these things give the lighting system a chance to see what's happening in the room. And then how do we take this information and how do we make it important for autonomous lighting control? And this line at the bottom about making light integral to the Internet of Things. Today's smart lighting is really just a smart socket. As I said, it's connected lighting. It's not really smart. But if we make the light properties an integral part of what is sensed, of things that connect to the internet that measure lighting properties, then we can start talking about making light truly smart. So the other thing that I kind of want to show here, and we'll talk a little bit more about this a little bit later in the presentation, is that we can harvest a lot of information in reflected light. Now, gaming designers are working on this in real time. And shown here is a graphic from UCSD showing an environment where to design this rendering, you have to understand a lot about light. You see the variation in the brightness of the light on the red wall and on the blue wall. You notice shadows. You notice reflections and focusing from this floating glass sphere. All the information that you need to know about the space is contained in the reflected light data. The colors of surfaces, the distribution of illuminance, the flow of light is required to create this scene, and object location and movement. In fact, people that design video games today are getting really good at understanding how lighting systems operate and how to create renderings of real illuminated spaces. And they do it very quickly and they do it in real time. All this information is in the light. What can we do with that information? So first we define something that we call a Plenoptic light field function. All this is that for us to be able to use the information in the light, we need to know the intensity of the light at any point in the room and the directions in which it's traveling, the wavelengths that it contains, and timing information when it's on and off, and any digital information it contains. And that's about as mathematical as I'm going to get in this presentation, but there's at least a mathematical formulation for what we call measuring this light, reflected light in a space. So how do we actually implement that in some of our facilities over here at LISA? So we have created a test bed. Our funding agency, the National Science Foundation, requires all of these kinds of centers that they fund to have fairly developed test beds. And what you see over here is a conference room that we call our smart conference room. You see windows, chairs, table. You see a ceiling containing sensors of different kinds. You also see that the lights are fully color tunable. And just because we don't really design light fixtures in our center, we contracted with Telelumen to use their Octa light fixtures that use 8 separate wavelengths that we control and define to create all kinds of spectral power distributions and metameric changes in the light for color dulling and color saturation effects. So we have the color tunable lighting. We have some black bars in the ceiling. You see them there. Those are time-of-flight cameras. Time-of-flight sensing is a little bit like indoor LiDAR, just like outdoor cars that are autonomous use LiDAR, light as radar, to find out where people and things are. We're doing the same thing indoors to be able to create 3-dimensional depth maps of where things are. And then if you look closely at the top picture, you see the small black dots. You can even see them in the bottom picture with the color lights. Those are simple color sensors. They're measuring the intensity and the spectrum of reflected light from the surfaces within the room. And we call that aspect light transport mapping. Let's talk a little bit about how much these things work, starting with light transport mapping. So our simple sensors in the ceiling just are looking at the color map of the room. Anything that changes the reflected color map is an object that's moving around or a new object that's been moved into the room. So in a very simple sense, the student who just graduated, in fact, with a PhD in advanced building controls using the sensing system, is disturbing the reflected color map, and so we know where that student is. Now, we can go one step beyond that and actually, at very high frequency, have each individual light broadcast a digital signal. And then by that perturbation in the modulated light, we can triangulate his location much more accurately to figure out where he is, whether he's standing or sitting, and how he's moving around the space. We can also do this with more people, but like some of the other sensing technologies for people and occupancy in spaces today, like RF attenuation, that becomes more difficult as the room gets more and more crowded. So we want to augment this kind of reflected light sensing with low-cost color sensors using simple indoor light or time-of-flight sensing. And that's shown over here on this next graphic. And what you see over here are people streaming into the room. You recognize the same student that was in the color mapping scenario. And what you see on the left-hand side are 2 images of a height map. You can call it a heat map. It looks like a heat map, but it's not having anything to do with heat. It has to do with how tall or short a person is, whether they're standing, sitting, or falling down. In the top image, you can see the table. On the bottom image, we've digitally subtracted that table just to take a look at how we can label individuals and see how they're tracking around the space. So what we've demonstrated that we can do with this kind of simple time-of-flight sensing is measure distance. And using that distance measurement, we can count occupants, we can locate them, we can take a look at their pose, their general orientation, we can detect falls, and we can do all of this very quickly. Now we combine this information with the reflected color mapping that I talked about earlier, and we can now create a lighting system that knows what its environment is doing. Ideally, we could do time-of-flight sensing with visible light and the same modulation I talked about before. In this particular example, we're using commercially available infrared time-of-flight cameras, but we've demonstrated that we can do the same kind of things with visible light as well. So now we have at least formulated the basis for a sensory lighting system that can know where its light is going. It can even know, based on reflected spectral power distributions, the colors of surfaces. It can recognize sunlight and know what the people are doing in a space. And so that's a starting point for creating autonomous lighting and control systems. Furthermore, we do this all without any radio frequency tools. And we do this without a camera. So it's completely privacy preserving. Subsets of these tools that we're now designing to be much less expensive can be placed in areas where people ordinarily expect privacy, like restrooms or showers, where, especially for taking care of the elderly or for hospitals, fall prevention and safety detection are really key. So that's what we're looking to do with these kinds of sensing systems. Really make them autonomous, but also make them such that they don't really use cameras and preserve occupant privacy. So we've taken a look at the occupancy and localization activity estimates that people are now using, and this has always been a very big area of research. You all know about passive infrared motion detectors, but you also know that they have problems with false positives and negatives. You know about heat sensing imaging arrays. They tend to be more expensive. Ultrasonic sensing can be used with passive infrared sensing. Commercial systems have been available for decades. For occupancy sensing that turns lights on and off, it is also prone to false positives. Recently, with RF technologies, you can give people RFID tags or look at their phones, but it requires that you tag everybody, otherwise you miss people. RF attenuation is a very interesting technology, simply putting antennas on the wall to figure out where people are and how the human bodies absorb RF energy. Of course, cameras can do it all, but it doesn't preserve privacy. And so we would argue that using light sensing technology, we can really precisely locate people and things dynamically, very low latency, and now we can use this to control the lighting systems. Steering the light, directing the light, turning the light on and off, making sure that it does what it's supposed to be doing pretty much autonomously without direct interactions with individuals. One of the things that we discovered while we were doing this work with the color sensors for the simple color field mapping is we can also use the color sensors to sense daylight intensity coming in from windows. And what this shows here is an identical system to our smart conference room that was installed at a hospital room at our partner school, the University of Mexico. In this particular example of this test bed at UNM, what we were really doing was using the lighting and the spectral power distribution of the light to do phase advance and phase retard of circadian rhythms in patients in rooms with sleeping disorders. But we demonstrated that we could also just take a look at the reflected light coming in from the windows, and we could measure how much energy was coming in from the daylight. It turns out that although this is only partially important to daylighting and lighting control using daylighting methods, it's really important for HVAC system control because the heat coming in from the sunlight can really impact feedback control of HVAC systems. And so what we found is that we can really measure this accurately just using our color sensors. So we can sense occupancy and solar energy gain for HVAC control using the same platform. So that's just a side benefit of what we can be doing. But it also shows that we can use our testbed technology in a healthcare environment. In fact, part of what we like to take a look at for our overall view of cognitive lighting is this interface of wearables, color control, sensing, to take a look at advanced physiological and neurocognitive processing, to take a look at how we control HVAC, lighting to improve sleep, take a look at task scheduling issues for improved health and wellness. And all of you know that with the well building specifications that are coming right now, a lot of people are really very interested in trying to establish a return on investment and a value proposition for wellness through lighting and other building controls. We'd formulate that lighting and health can be important to improve worker performance. People are starting to do more research on that. But mostly what we can do now is talk about a fully evidence-based engineered system that again lends itself to lighting controls that frankly are going to become so challenging for mere mortals to control. They pretty much have to be autonomous. Controlling spectrum, intensity, energy balance, reporting functionality. These are all things that lighting systems can do autonomously with the kind of sensor systems that we're talking about developing. Now, where do we go with all this from a design perspective? And one of the things that's been very important in developing very advanced manufacturing systems and troubleshooting systems is the concept of digital twins. If you remember that image I showed earlier on with gaming, people are now starting to use virtual reality and augmented reality to create digital twins. And we propose, and other people are now exploring, using digital twin concepts for lighting design and control. So what would that mean? Well, I would have a gaming engine into which I would import design data. What does my space look like? I would import IES files and spectral power distribution information from the lighting system. So now when I put my lights in there, the rendering gaming engine will automatically illuminate the space. I can import daylight data. I can import surface reflectance data. What's the color of my paint? What is the color of my wood? All this stuff can be imported now and simulated. And I can even simulate human activity. So we're experimenting with these digital twin designs for creating autonomous lighting systems. And it's a very powerful technique that I think is going to have dramatic impacts over the coming years on the entire lighting design industry. So what I'm showing here is a picture of our office suite at LISA at Rensselaer Polytechnic Institute. We have hanging troffers. We have office doors. We have kind of a yellowish wall color. So we want to simulate this space now because we're actually installing sensors in this space to figure out where people are and how we can control the lighting. So we have our experimental time-of-flight sensors. They're much lower cost than the time-of-flight cameras. We're using a Unity digital twin concept. Now, Unity is the name of a video game development engine. So we use Unity to create this virtual environment where we want to take a look at how we use virtual reality tools to visualize the environment. So let's take a look at what that looks like from a sensing perspective. This is the Unity gaming engine with simulated human beings. What you saw on the ceiling are our time-of-flight sensors. And every time a person interrupts a beam from our time-of-flight sensors, it measures the distance to that person. We use this kind of information to train our sensors to recognize who is walking where. We can't identify who they are, and what they look like, and what their direction of travel is, and what their movement velocity is. If they fall, we can detect that in a simulated environment. We use this to train the environment. Similarly, if I put my lighting system into this same simulation, along with the IES profiles for the lighting system, I could dynamically adjust the lighting environment to take a look at how the space was illuminated. And we've tried to be accurate in terms of the colors of the walls and the reflected spectral power distributions. So this is an example of how you can actually do a gaming engine with simulated people to create a virtual environment. And I think that this is going to have a dramatic impact on the future of lighting design and even architectural design, I think, in the following ways. And so when we want to take a look at what we can do with digital twin creation as a lighting design tool, we start off in the middle with a 3D gaming engine. I put my architectural designs in. I know where the windows are. I can simulate sunlight. I can simulate whether or not windows are north-facing or south-facing. I can even simulate cloudy days very easily. I put in interior design input. So I create my virtual space. Now, somewhere on the cloud, I have some kind of a SKU lighting design sorter and selector. The simulated system searches the cloud for every lighting fixture ever made and figures out how to realize certain kinds of lighting profiles. It simulates sensors and controls that can be put in the space. It now puts that information back into the rendering engine. We put virtual people in the rendering engine designed for whatever space they happen to be, whether it be doctors and nurses and patients in a hospital, people living in a home, workers in a workplace, workers in a manufacturing environment. All that goes to the virtual reality tool suite. It autonomously learns what people are doing and what the data feedback approaches are for controls in lighting design and lighting optimization. It even can simulate energy calculations. It goes through and continues to operate and optimize that. The lighting designer can step in at any point and using augmented reality or virtual reality headsets, take a look at how this actually looks and use their own trained eye to figure out whether or not the design is optimizing in the right direction. And what pops out at the very end would be a finished design. Lighting design, architectural design, paint and reflectivity. All this information can be downloaded into the simulation tools. Now, this is starting to happen now, and these tools are going to continue to become more and more powerful. And so I think we're going to see this migrating faster and faster into the architectural design and lighting design space. And because we can add lighting design and sensor designs, we now have a powerful tool for autonomous training of the system. So the machine learning can now be applied to optimizing the overall design process. So what this will essentially do is to take data from IoT systems and be able to allow people to visualize it in ways that will simplify the overall design process. And just to show that this is happening very, very quickly, I wanted to pull up a very recent paper that shows the power of the simulation capabilities, where researchers at North Carolina State University in Raleigh and in Charlotte have published a daylighting simulation where they've assessed circadian stimulus in the lighting system in office buildings coming from daylighting completely by simulation, where they can use the same kind of gaming engine. In this particular case, they used Rhinoceros 3D or Rhino 3D. We use Unity, but they were using Rhino with a lighting design tool called Diva with an alpha plugin that calculates spectral reflected power distributions. And they could actually simulate the ocular light dose at the worker eye. These kinds of tools now can be used to not only estimate what the exposed spectral power distribution is for workers in a place to assess circadian stimulus. It can even be used to evaluate glare metrics for lighting systems, because you can simulate all of this stuff using these powerful tools that are being developed and are now being used by designers to start taking a look at how these tools can be applied to lighting design and even human factors problems. So this is coming, and I might say it's coming pretty quickly as people take a look at how to really automate some of these processes to simplify lighting and architectural design. So what's IoT got to do with all this stuff? Well, we all know that the Design Lights Consortium is putting out their technical version 4.0. Technical version 5.0 will be due about a year from now on what network lighting control systems typically require. But a lot of people complain about IoT because it provides data. It doesn't give you any information. So a lot of sensors generate piles of data, but you really need intelligent software to process that data into information so that you can have actionable results to be able to control buildings, control lighting, improve people's lives, meet their needs, and so on. So this is where smart really is. Smart is not in connected lighting. Smart is not in IoT. Smart is really in machine learning. And so the last thing I want to do is kind of connect the dots between IoT and machine learning. And you might be able to say that there's kind of an analogy here. If I want to read a book, I have in my language of choice pages full of letters that are organized in a way that I can understand them. You might say that IoT is just the letters on the page. But to organize them and understand them really takes a machine learning approach. How do I take random sets of data from a given space, now process them in a way that an intelligent agent can figure out how to act on that data? How do I convert data to information. And these are things that people are developing on the computer science side in real time. And we're starting to take a look at this in our own smart conference room. And as I said, the IoT is data only. We need semantics. We need context needed for machine learning and artificial intelligence. And so what you really need to do is to take all of your sensors and all of your lights and even your HVAC systems and your other sensors and create semantic data dictionaries so that a computer agent, a computer program essentially, can understand the data that it's looking at. And this is a lot of drudgery. It's a lot of tedious work. These kinds of semantic data dictionaries are being developed now very rapidly for electronic medical records for healthcare systems. They're also starting to be developed for building control systems. They're starting to be developed for industrial manufacturing systems because we don't want people writing software on a case-by-case basis for intelligent controls based on data. We want generic machine learning programs that can come in and say, open the data book, figure out what's going on, and provide information for people and for systems automatically. And this work is also taking place in real time right now. So you might say IoT provides values. Semantic data dictionaries talks about the meaning of those values in terms of objects and properties. And so if we merge virtual reality and augmented reality with semantic data dictionaries and IoT, we now see that we are coming up with models that allow us to create systems that think. Not only systems that think, but also perhaps lighting systems and buildings that think. Autonomy will continue to creep in to our systems that we have that control lighting and lighting design and even buildings. So at this point, I'd like to summarize what we've covered in this talk, or what I've covered in this talk. We want to make lighting central to sensing and control. We want to be able to develop digital twin concepts to really explore autonomous system design and train smart lighting systems so they can learn autonomously as to what they need to do to meet the needs of people. We need to remember that smart means a lot more than just IoT and connected lighting. And I think I've highlighted that some transformative changes to the lighting industry as a whole are only now just beginning. We see application in this space in what we call cognitive lighting systems, energy efficient buildings, light communications for 5G applications, adding light to RF telecommunications. Of course, healthcare for health and well-being and wellness, and even in what some people might call cyber-physical farming, where sensing the light and light reflection from plants and even the light that plants emit can be used to control the lights for improving horticulture. Truly autonomous systems that fit into all these different market demographics. And that's really what we're looking to try to develop here at the Center for Lighting Enabled Systems and Applications. Again, it's more than just lighting. It's lighting that enables systems and advanced applications. So finally, I'd like to acknowledge the people that have made this work possible. First of all, our funding organizations, the National Science Foundation and NISTAR, and also some funding for NYSERDA, although I don't have their logo on the slide. Our partner schools, Boston University, University of New Mexico, and Thomas Jefferson University. Our industry members who actually pay us to join to take a look at what we're doing. And of course, our faculty and students. I'm just reporting largely on their work. And I've been privileged to be able to learn so much from them and taking a look at where the industry of lighting as a whole might be headed. So if you have any questions or want to learn more about Lisa, feel free to reach out at any time. And with that, I'll close, and I'll be happy to take any questions that have cropped up during this presentation. So the first question is, how much evidence do we have of IoT being applied to lighting itself? So IoT can report lifetime energy use, color, dimming. It's a really good question. I think that the DLC requirements for connected lighting now increasingly require lights to report energy use. This is probably most advanced in terms of street lighting now, where requirements for what I believe is called smart lighting, although I really call them smart poles, require the fixture itself to report things like, well, power use, report whether it's on or off when it's not supposed to be, failure, and then sometimes the street light fixture is given other sensors, cameras, daylight sensors, and things like that. So gradually this is starting to come into play. But again, the light doesn't really know anything about its environment. It can just report energy. So this is starting to happen more and more. So I think that we're starting to see this. We're still at the very beginning phase. And one of the liabilities of really trying to drive it faster is that a lot of different companies have their own communication systems. And we have a lack of interoperability between systems, and that is slowing progress on connected lighting. The next question deals with whether or not we'll have to wait until we get to level 5 for full BMS integration. Interoperability and proprietary designs is another can of worms that needs to really be sorted out by the design community. And I think that probably, yes, we're going to have to get to that point as more and more people take a look at what we really need to have in buildings in terms of sensor technologies and sensor reliability and data processing systems to make building management systems really smart. If we do this job right, the systems can evolve together to be able to really integrate lighting and controls. Now, clearly some of that is happening now. There are building management systems that have integrated lighting controls. But I would make the argument that they're usually proprietary. Lighting controls are still problematic. Commissioning them and maintaining them is a problem in many cases. So we're going to have to embed more autonomy before that can become real. The next question over here is, as lighting becomes more intuitive or autonomous, will the role of standards and recommended practices be changing to follow suit? That's a really good question, and I'm not necessarily sure I have a good answer for that. The standards and recommended practices, I believe, are very well established, continue to evolve based on what we understand about human factors and what lighting spectral power distributions can do. So I think the standards and recommended practices will be the same nominally, but they will plug into automated integration processes that will help automate the design process. And so I think that's where the major change we see will be. The only other thing that we would say would be that perhaps for commissioning, some kind of a digital twin concept in the distant future may be required for large lighting and building system installations. So another question, how many years away are we from when we think typical architectural engineering firms will be using VR and digital twins for lighting design? It's here now. A lot of the big architectural firms are starting to experiment with these things. The tools are becoming more and more powerful. It's the province of architectural design at a lot of universities with schools of architecture. So it's coming now. I think it's going to happen a lot more quickly. And I think that probably over the next 5 to 10 years, it should become a standard practice in a lot of big program designs. Another question, do you think that data collection strategies and circadian lighting strategies infringe upon legal limits on the invasion of privacy? Another good question, and I'm not sure that we really have a good definition of how people would opt in or opt out of sensor systems that infer circadian performance. But to a certain degree, I believe it's not that important of a point. I tend to fall back to Lockley's definition of a lot of blue light in the daytime, not too much blue light at night. So many other things impact sleep and circadian function that are not light related, that I think that it becomes a much more complex issue. And to first order, the lighting systems will just do what I would say baseline spectral power distribution for normal daytime, nighttime lighting recommended practice. So to a certain degree, privacy invasion should not be an issue. So with that, I hope that this has been an interesting concept of why I think that smart lighting as it's envisioned today is really just a myth. But like a lot of myths, or perhaps futuristic views of where technology is going, I think that we can take a look at how things like augmented reality, advanced sensing networks, semantic data systems, and machine learning are going to revolutionize lighting, integrate building design, and automate design processes, and even lead to ultimately embedded lighting designers in lighting systems and buildings of the future. And with that, I'd like to thank you for your attention.
And on behalf of the Illuminating Engineering Society, I would like to extend our sincerest gratitude to Bob for this really outstanding presentation. Today's presentation has been recorded and it will be made available in the IES video archives in just 2 weeks' time. Available to members only. If you are not a member of the IES and would like to access this archive, please contact membership at ies.org for more information. Did you know that the IES has a brand new podcast channel? IES Go can be downloaded from your favorite podcast provider and currently offers 4 separate programs. Forces of Change with Mark Lean, Trailblazers and Icons, Lights of the Round, and Architecture for Light. Check out your favorite podcast provider or just type in IES Go podcast into your favorite search engine. They're perfect for your flights, your commute, or whenever you're on the go. Registration for the IES's annual conference is almost sold out. If you are interested in joining us on August 8th through 10th in Louisville, Kentucky, head on over to ies.org and click on the annual conference link underneath the events tab to lock in your attendance. Space is very limited and is nearing capacity, so do not hesitate. That will wrap up today's educational webinar series event for the Illuminating Engineering Society. My name is Shane Skwarek. I thank each of you for spending the hour here with us and hope you enjoy the remainder of your day. So long, everybody.